Your voice.
Hello. Yeah.
Okay.
Okay. Welcome back, everybody, to this afternoon session of our inaugural conference of La Sol. For me, it's a pleasure to introduce Ferrán Valdez from Centro de Ciencias Matemáticas from Morelia, who will give us a trilingual talk, Taffy Pullers, Panadería, and Le Vent dans les Arbres.
Thank you very much. Thank you very much to the organizers for giving me the opportunity to speak at this event. And so I will try to do sort of the same thing that Adem tried to do in the last talk, that is give you a taste of the kind of mathematics that we do when we get support from programs like LISLA or UMIs around the world. And when I say we, it's me and the collaborators that I put there in the corner. So let me start by showing you what I mean by a Taffy puller. And instead of explaining that, I've chosen a video that I want to show you. I'm going to comment as the video plays. And the important thing that you have to pay attention on this video are two things. First, how do we make Taffy? And second, there are some machines appearing. And the mathematics I want to explain are behind these machines. So let me show you the video. So the video, it's a video that happens in Texas, in a fair state. And what you're seeing is a place where they claim to make the freshest taffy in the world. It's a place called Sutter. So how do you make taffy? We're about to come. Taffy, you get 12 pounds of corn syrup. You mix this 12 pounds of corn syrup with 7 pounds of sugar. You add butter. You heat that up, and then you end up with a mass that is really hot and really sticky. So you have to cool it off. And for that, you put that on a slate to cool it off. And then you end up with a sweet mass of sticky caramel that is too hard to be eaten. So in order to make it eatable, you have to put air on it. And to do that, you fold it, stretch it, either with your hands or by putting the mass on this machine.
Oh, it's a measured lamination.
Yeah, it's a measured lamination. But what I want you to see is just this machine and the way we are mixing, folding, and stretching the taffy. And well, that's a Taffy puller, and that Taffy comes in different colors, and it's really tasty. So the video goes on and on, but I'm stopping because there are some other machines coming on. And now that I have your attention, I want you to draw your attention to a really nice paper by Jean-Luc Tifo, which appeared last year, on July of last year. And this paper is called A Mathematical History of Taffy Pullers. And I want to draw your attention on this because Taffy pullers are relatively old. You can trace their origin back to the end of the 19th century. So I'm going to scroll down this paper and show you just the pictures, not the mathematics, just the pictures. So there's an introduction, blah, 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 acknowledgements, some history, a lot of name dropping, what. And then you come at the first picture. This picture on the left shows an image of, as I think an engineer could understand, and on the right, the mathematical interpretation. This is a patent by Ferrán from 1893, which is a really inefficient Taffy puller. And as you go down on the paper, you will see different tries of humanity to invent the perfect Taffy puller machine. Second one actually mixes well Taffy, but it was really difficult to build. And so on, we continue. There's another one. Who said measured laminations? Okay, there are the measured laminations. You see the train tracks on a patent for this Taffy puller from 1908. Thurston was not born, but you know.
Well, that's how Sullivan used to tell us about or describe measured laminations. He would say, "Oh, it's like a taffy machine."
I didn't know that. Thanks. So an homage to Sullivan. Anyway, I want to draw your attention to the fourth figure of the paper. And in this fourth figure of the paper, I'm going to stay a little bit of time. On the right-hand side, on the upper part, you will see a diagram that I guess an engineer can easily understand. But me not being an engineer, I found a video to explain you the machine that we're about to analyze. So the video is the following. No, it's not this one. It's this one. So you're about to see a machine that has 3 rods, say 1 to 3, and the machine turns the rods 1 and 2 clockwise and the rods 2 and 3 counterclockwise. This is the first example of an efficient Taffy puller. that's how the mechanism works behind, in case you wanted to understand how it works. So this is the Taffy puller machine that I want to analyze right now. So I'm going back to the picture of the paper by Tifo, and this is the machine that you have on the right in this diagram. The mathematical interpretation of this machine, many of you probably have already guessed, is a homeomorphism of the three-puncture disk that takes the three punctures, 1 through 3, and turns the punctures 1, 2, say clockwise, and then 2, 3 counterclockwise. And I want to concentrate on this example to convince you of the following fact. So fact is the following: attached to each Taffy puller, there is a number that records the exponential growth rate of the length of the candy mass we're pulling. I'm terrible at verbalizing things, but that's what I want you to convince you. So what's this number? So the idea is the following. So we are in a homeomorphism of the three-puncture disk, and probably you have realized that we can go down from dimension 3 to dimension 2. And now the mass that I show you in candy is actually a curve that I will put around the punctures 2 and 3. And let us suppose that this curve here, by say some metric that we put on the disk, has length 1. So we put length 1. And I want to see how the length of this curve grows as I turn on the Taffy. So I turn 1 and 2 clockwise. So this becomes a longer thing, which is roughly of length 2. And this one, when I turn then the rods 2 and 3 counterclockwise, you'll probably guess is approximately of length 3. How do I see this? This is approximately twice, and then I see these 2 copies here and then 1 copy here. So if I go down here, I will see probably 1, 2, 3, and then here 1, 2. So this has roughly length 5. And then down here, if you zoom in and you do the calculations, you will see that down here, the approximate length of this curve is 8. I know, I'm surrounded by really well-educated people that recognize Fibonacci like that. So yeah. Couldn't get sexier, I know. So anyway, my point here is that let us make things more precise. So what I mean by exponential growth rate is that if you name your curve gamma, and you name your Taffy puller the homeomorphism h, then if you measure the length of the nth iterate of gamma, divide that by n, and you take the log, and then the limit, you take here the log, and you take here the limit as n tends to infinity, this number will be a number lambda, which depends on h bigger than 1, and this is what I'm calling the exponential growth rate. So this number appears in this formula like this. And if you are bored, I invite you to calculate the number in the case of this Taffy puller. So now that I have convinced you that there are interesting numbers behind this, I want to say that this is just it's part of a more general phenomenon. So this fact can actually be transformed into a theorem. So let's call things by their name. Attached to each Taffy puller, I'm going to change Taffy puller by a homeomorphism of the punctured disk, just for the sake of an example. And these homeomorphisms, when the Taffy puller is effective, have a really special name, which is pseudo-Anosov. So to each pseudo-Anosov homeomorphism, attached to each pseudo-Anosov homeomorphism, there is an algebraic integer called the dilatation that records the exponential growth rate of the length of, and I change candy mass by a curve under iteration of h for any given metric on the disk, or say in any surface. And this is not a fact, this is then a theorem, and I will attribute this to Thurston. So that's how I see Taffy pullers, and now you might ask, well, what can you do with them? So, no, this is not what I wanted to show, sorry, spoiler. So going back to my talk, what we can do with Taffy pullers is something really, really nice. We can go from dimension 2 back to dimension 3, but not back to the real world, but back to the world of hyperbolic manifolds. So when you have a pseudo-Nosov, you can take the suspension of that guy. The suspension is just what you see here, is S cross 0, 1 modulo this relation. I call that MH, and there is this beautiful theorem by Thurston telling you that a homeomorphism will be of this type, this Taffy puller type, this pseudo-Nosov type, if and only if the free manifold that you get by suspending the guy is hyperbolic. Meaning by that it has a constant metric of constant curvature -1. Okay, so far so good. Now, a trivial but really important remark is that by construction, when you suspend the homeomorphism, you get for free a fibration over the circle. The fiber is the surface on the where the homeomorphism lives, and then since you're identifying on 0, 1, 0 with 1, you get something at fibers over the circle. And this allows me to say,
you have a missing H.
I have a missing H.
H of S.
0 with H of S, comma 1.
Oh, yes. Sorry. I know. This makes no sense. Here goes H. You're right. No, but I have to put the H on the right? Yeah, you're right. Thank you, Santiago. Here you should put an H. Or yeah, same. Anyway, my point is that you can think of Taffy pullers now as cohomology classes. So let me convince you of that. Once you have a fibration coming from a Taffy puller or a pseudo-Nosov homeomorphism, you can put the form d theta on the circle and you can pull it back to the tree manifold. This will give you a cohomology class here with integer coefficients. And so there is a natural question because there are many, many cohomology classes in some three manifolds. And the question is, well, actually, if I just look at the cohomology of the tree manifold, how many integer points in the cohomology come from fibrations? So in the language I'm developing, how many points in the first cohomology group are actually Taffy pullers? And then the answer is an answer given by Thurston, which tells you that if the tree manifold has enough topology, meaning by that the first Betti number is at least 2, and the right conditions are met, and I'm not explaining right conditions because of time, then infinitely many integer classes here come from fibrations over the circle. And moreover, if you just think about them, they are not randomly scattered on cohomology, but they form a really beautiful coherent picture. So I'm going to show you the picture for the example that I just developed. So the example was this three-rod, this homeomorphism of the punctured disk, or the three-punctured disk. If you suspend the homeomorphism, say in the language of braid group sigma 1, sigma 2 to the -1, you get a hyperbolic manifold, which is the complement of the link that you see here. Well, you see two links, but there are two manifestations of the same guy. And if you are not theorist, you probably know Rolfen's table, this is just the link 622. Anyway, I have chosen this one because in this case, the first Betti number is 2. Because homology is generated by meridians, and this guy has clearly just 2 components, the link. So first Betti number is 2. So I can think of cohomology with real coefficients as something in the plane. And so here I put a picture of the plane, and the black dots that you see here are the cohomology classes that correspond to fibrations over the circle. And they appear, Sorry?
Mataste la torsión.
Maté la torsión. Yeah, thanks. I'm supposing there's no torsion,
Yeah,
but
nada más por precision.
I know. Yeah, so they appear inside a cone whose basis is a face of a polygon that corresponds to the unit ball of some norm that we put on cohomology called the Thurston norm. But if you don't understand, it doesn't matter. This is how they appear, the vibrations. And so I have a lot of Taffy pullers. And so for each integral point in the picture that you see, we have a pseudo-Anosov homeomorphism because the tree manifold was hyperbolic. So if you get another vibration and you take the fiber and you go around the circle, this will give you a homeomorphism that is pseudo-Anosov. So behind each of these points, there is a number to be computed. And there are interesting questions on number theory related to these numbers. So to sum up, the contribution of the work that we have done, and this is with Erwan Lano, is that we developed an algorithm to effectively compute these dilatations. And when I say effectively, I mean that we have written a pseudocode that can be implemented in, say, Python or C or whatever, put in the computer, and compute actually these numbers. And so that's everything I want to say about Taffy pullers. I cannot explain how and what are the elements that we use without more time or more name dropping. So just want to pass the idea of our contribution. We compute dilatations associated to Taffy pullers that appear in three hyperbolic manifolds.
So here the dilatation, I guess, is either the golden mean or log of the golden mean?
No.
No, in this example.
No.
Oh, what is it?
The golden mean appears as the limit of the quotient of the n plus 1 term, but that's not my formula.
Okay. Tell me what you get.
At the end of the talk.
Okay.
I can give you a hint.
No way.
Anyway, I only have half an hour. So let's breathe in and start talking about whatever. So the word in English is wind tree model. It has been translated to French as le vent dans les arbres. I don't know why. I didn't do the translation. But I want now to talk about wind tree models. So wind tree models. What is a wind tree model? WTM. A wind tree model, well, they're also rather old. They were first introduced by Paul and Tatiana Ehrenfest at the beginning of the 20th century. And the model that I'm presenting now is part of a bigger family, which this model was introduced by Hardy and Weber in the 1980s. So a wind tree model is basically a billiard that takes place on an infinite table. So it's a billiard on C2 times some obstacle, rectangular obstacle of size A times B. That is what you see on the picture. So the blue things that you see here periodically put, like if they were on an integral lattice, these are the obstacles. They are of size A over B. You chose A over D so that they don't overlap. And now you put a little point, and then you play billiard with it. I've been explained that the idea is that these guys are the leaves. And so this point is supposed to be a representation of a gas molecule going through the leaves. It's a really oversimplification of a Lorentz gas, but anyway. So you go, play billiard. When you hit something, angle of reflection equals angle of incidence, and then, well, this point goes around, lives its life, and you have a nice dynamical system on which you can ask many questions. So now what I want to talk about is how you study this dynamical system. Because
Only two slopes possible?
yes. In this case, yes. But if you imagine that the obstacles were randomly put and were not parallel to, so no. But in this case, yes. Good observation, by the way. So how do you study this thing? So let me call the billiard table TAB. And the idea is that to each billiard table, you can associate using what is called an unfolding trick, a surface, which has a special name. So it's a translation surface on which the billiard trajectory becomes a geodesic. Let me explain this. Translation surface is a surface on which the change of coordinates are just translations. And they have a natural flat metric, and you can think of the geodesics with respect to this flat metric. But this translation surface has some special topological flavor, which is the kind of objects that we study. This translation surface will be of infinite genus and one end only. So this is what we call an infinite type translation surface. It's just a surface with infinite generated pi1 on which you have a nice change of coordinates. And so let me just roughly explain how you associate to a billiard a translation surface using an unfolding trick, just to get the flavor. 2 minutes. It's difficult to explain on an infinite billiard. It's rather easier to explain it on a square. So the idea is the following. When you have a billiard trajectory and you take a side, say on the square, and the ball collides with, say, the side B, you can, instead of reflecting the trajectory, reflect the table. So the shadow of the trajectory after the collision on the reflected copy will form with the segment of the trajectory before the collision a straight line. And so you can continue this unfolding process in all possible directions, but there is some redundancy here because I've never chosen an origin. So if after doing a lot of reflections, I encounter a copy of the square that I started with that differs, say, with this square by a translation, I should identify them. And this is how you get a translation surface structure. This process, applied to the table of the wind tree, gives you an infinite type translation surface of infinite genus and one end. Okay, now, as many probably of you know, it's rather difficult to study dynamical systems in this regime because here we have infinite area. And so if you want to do dynamical systems, you don't even have Poincaré recurrence. So what can you do? Well, because of the periodicity of the billiard table, this infinite translation surface actually covers, say, a finite genus translation surface. In this case, will be a translation surface of genus 5. And the monodromy group is, sorry, the covering group, you can compute it, is just the integers times the integers. And we know a lot about geodesic flows for finite type translation surface. There's a whole tribe of mathematicians that have studied this for decades. So we know a lot about them. And we can use the covering group, and for the experts, the keyword here are skew products, to pull results from the dynamics downstairs, upstairs. And so doing that, we can prove theorems. I mean, not we. So here are some questions before going to the theorems that you can ask about the wind tree. Does the particle come back? How far goes the particle up to time t? Does the trajectory go everywhere? How do these properties depend on the initial point, the initial direction, the size of the obstacles, etc., etc., etc. And so, so let me mention some theorems on the wind tree, which are not mine, but I found them really interesting. So the theorem is, it's a theorem like typical in dynamical systems. For almost all parameters, for almost all directions, and for almost every point, you can say things like the following. The billiard is recurrent. And so the first ones to prove that, well, were Hubert, Lelièvre, and Trubetskoy. And then they prove it in a less general way. And then Avila and Hubert put it in this form. And by the way, they got to work in the EMU in Rio de Janeiro. So this is a theorem product of EMU. And then, sadly, the geodesic flow on this translation surface that you have here is neither ergodic nor minimal. Something weird in between. And these are resolved by...
The current piece that it comes back arbitrarily close to?
Yes. Yes, you can actually program these things, and I have more pictures that I can show later, and see recurrent trajectories. So this is another result on the geodesic flow. It's neither ergodic nor minimal. You can ask things about periodicity. There are some other works by Hubert and so on. And so this is what I wanted to say about the wind tree. We're currently working on a project that involves a book on infinite type translation surfaces, and these are the objects that we study in this regime, infinite volume. So how much time do I have left? 5 minutes, perfect. So this brings me to the last part of the talk, which is panadería. Panadería, how do you translate that? It will be bakery and patisserie. So it's a delicate subject. If you know French and Mexican history from the 19th century. But it's really fun. So let me say something about panadería, and for that I want to draw your attention to this paper. So this paper is called, has a fancy name, a hyperelliptic realization of the horseshoe and Baker maps. So it's by Chamanara, Gardiner, and Lakik, and as always I'm going to concentrate on a picture to show you how behind the process of kneading the dough there is an infinite type translation surface. So I'm going to scroll down until I hit the picture I wanted to show you. And here's the picture. I'm going to explain more or less what's the idea. So kneading, I think the translation in French is pétrissage, when you're doing the bread. And in Spanish will be amasar. Amasar la masa del pan. So the idea is that you have the dough here. The dough is a rectangle formed by two squares, y0 and y1. And you want to make bread. So when you're mixing the dough, then you take the top half, say, of that thing, and then cut it off, put it to the right. So y1 goes to the right, and then you glue them back together, stretch, compress and then stretch to come back to the original form. This is what is called the Baker map. So it's a map that goes from, say, y tilde, which is a union of y1 and y0, to y tilde, and this map will be f tilde. This map is really nice. It has really a small problem that is not continuous. It's evidently not continuous because you're cutting the dough. So how to make it continuous? So you end up in a regime of topological dynamics or whatever. So the idea is to make identifications on the border of your dough, in this case of the rectangle, and these are the identifications that I'm going to explain. So in order to make this thing continuous, you take your rectangle and say I draw here the top side of the rectangle. And you will start dividing the rectangle by the factor, in pieces that have to do with the factor in which you stretch and pull. Here, suppose that the factor is 1/2 and 2. So you will divide the top side on half, and then from left to right, then 1/4, then 1/8, then 1/2 to the n. These are the segments that you see here as I1, I2, I3. You do the same on the bottom, but now from right to left. And you identify segments, parallel segments of the same size, using a translation. And you do the same on the vertical sides. You start dividing following a geometric progression, and then you identify this one with this one, this one with this one, using translations. And so, believe me, the quotient that I will call y is a place where you can pull down the Baker map, and it's well defined. Modulo that you have to take off the extremities of the segments. Okay. Now, it's not the Baker map that interests me. What interests us is this surface. I could have said nothing about the Baker map and just say, take an infinite polygon like this one. These are the sides, and identify these things using translations. This guy here is also of infinite genus, also has only one end. So it's the same thing as the wind tree, but it's area, say, 1. So in this regime, you are closer to what are classical dynamical systems. At least you have Poincare recurrence. And you have many other tools to say things about the geodesic flow on this surface. What do I mean by geodesic flow? It's just putting a point here and then fixing a direction and trying to follow it. And say something about the behavior of the point. Say in the vertical directions, for those of you who already know dynamical system, it's easy to find von Neumann's odometer. So it's easy to prove that in the vertical direction the flow is ergodic. But for a typical direction, we don't know anything. And so this is like in the frontier of infinite type translation surfaces. And I think I will stop here. And thanks for your attention.
Any questions?
I mean, for finite genus, the stretch factor is an algebraic number. It's actually a Perron number, I think. No?
It's a Perron number.
What happened in infinite genus? You don't have the same theorem.
What's a pseudo-Nosov in infinite genus?
But maybe you define it the same way. There are two foliations, in one stretches and one contracts.
Yeah, but then, okay, yeah, you can do that.
Yes, I mean, you take a pseudo-Nosov on the surface of finite genus and lift it
to the, yeah.
Genus. But that's one example.
But then if you want to copy things, I mean, these stretch factors, you get them by looking at the action on homology. And you get a big matrix, a Perron-Frobenius matrix, and then the...
I don't know, it's a question, because I think everything is open, no?
I don't know.
So how would you define it? Or, I mean, is the suspension still a hyperbolic manifold? If you are able to define pseudo-Nosov...
I can cook up examples where yes, but in general, I don't know. What are the analogues of Thurston's theory in the infinite genus?
Nothing.
We're still working on that.
I asked that question to McPaulin, and he said nobody knows anything.
No, we don't. We're scratching. We're scratching the theory little by little. And yeah. By the way, for those of you who haven't, I'm going to make some free publicity on my collaborator, Lano. If you can read French, in the last number of Gazette des Mathématiciens, you have in the section Raconte-moi by Lano, what is a pseudo-Nosov? And it's a really beautiful paper where you get your answer.
So it's almost...
It's close to the golden mean, but...
Because that power, it's log of Hn, where Hn is going to be the Fibonacci sequence.
I'm not
in
sure.
Your example. But that's a power, essentially,
of the Fibonacci number?
No, the Fibonacci numbers approximate powers of the golden mean, since you're taking a logarithm.
Okay, yes. Yeah.
The logarithm.
Any questions? We'll listen for them again.